a few scenarios, which means derived information about the phase excitation. This page basically summarizes what we have here. And so here, this is our problem statement. We have the one single degree of freedom, and on the base is moving. Here we assume the base is moving in harmonic in sine omega t. And this is our equation of motions, okay? And the first one, I think this page will be even better, okay? So the first scenario we want to know is the displacement transmissibility, and how to define it. That is defined as this. Since I use a different notations, let me modify it into what we have here. Okay. So let me modify here quickly. So this is what we have. So this is steady state response here, corresponding to the base excitation. So this equation simply is what we have here. Okay, that equation is simply what we have here. So capital X is this one, and phi is this one, and I simply summarize here. Okay. Because I just revised the slides this morning, I don't think you have updated one. Later I will just print out these few pages and upload separately into the lecture notes there, so you will have the same. So that is what we have. And then the first one, we define the displacement transmissibility. Basically, that is a ratio. That is a ratio between the response to the given input. That's the definition. Okay, so this one determined is defined as we call the displacement transmissibility. That simply is a ratio between the response and the input. The response is the response, this one, input is this one. That's it. Graphically, this term can be described in terms of this graph. And the reason why I put the graph here, because this graph is different, a little bit different from the previous one we've seen. And even for me, and sometimes I confuse. So I like to have a good note with me. I know which graph corresponding to which equations. I keep that one on my own. Okay, so this is the graph, and when you apply the graph, pay attention to the information on the y-axis. Okay, don't don't misuse them. And this graph showing is this equation, the phase angle corresponding to the different zeta, different r. So that is the one. This equation is for this one. Okay. And the example is, we might look at this example here. For example, if we have an omega and we have a natural frequencies, so from there we can do a little bit calculation. So if given omega equal to 5.82, omega n equal to 18 point something, so therefore the r will be equal to omega divided by omega n equal to 5.82 and 18.26, and that is equal to 0.318, about 319. Okay, so in this way, we want to calculate the displacement transmissibility. Again, we simply want to calculate the ratio of the two guys. and that's simply plugging into this equation here. Very straightforward. So we simply plug in into this. And that one, oops, seems I forgot one more piece. So for this equation, if you manipulate, you divide numerator and denominator both by k and work a little bit, and you can have the expression like this, just like we're showing here. Okay, so no, yes, capital Y still here. Thank you. Yeah, good. Okay, so this one basically we adopt using this equation: 2 zeta r and square and 1 minus r squared plus 2 zeta r squared. Okay, so with the zeta equal to, for this given example, 0.5 and r equal to 0.319, you simply plug in into calculation, and that will be 1.10096. Okay, and again, in my answers, I have a spreadsheet being built up. In that sheet, I have all the equations there, because once I know n, c, and k, I plug in the 3 numbers, and the spreadsheet simply gives me everything I need. I simply carefully looking into which cell that is the number I'm looking for. Okay, so basically I kind of gradually expanded the things. So this is a simple applications of the first scenario called the displacement transmissibility. And the second one we're going to look at is how to determine the magnitude of the steady-state accelerations. The previous page allows to estimate the steady-state displacement. So, which means if you sit in your car, you drive through a bumping road. That equation, if you know all the given informations, the previous slides allow you to estimate how, if you wouldn't tackle the safety belt, then the previous slide allow you to see how high you can jump. Okay. These slides allow you to see how quickly you feel the force being moved. That is this slide. Okay. Accelerations. So accelerations, basically the concept is this. We know this response. This is the displacement response. So in theory, acceleration simply is take the double derivative. After double derivative, then we see this omega square will be coming up. So the magnitude of the acceleration simply is very easy. Omega square multiplied with displacement. We already have the displacement from the previous slides. We simply multiply omega square. So that's it. Okay? Whatever the omega you plug in, multiply square, multiply with displacement from the first page, that's the magnifications. So under these situations, then again, you simply multiply the magnitude, that is displacement magnitude, with omega square, and that is the number for the accelerations. So you put into our equation in the previous slides, then that is the one we need. Okay, and I designed, not posted yet, but in the final homework, I'm going to post it over this weekend. And there's one question, so likely you're going to use the slides, that you're going to use in these slides. Okay, because in that problem, I asked you to calculate the accelerations. The third one about the force transmissibility. The force transmissibility is this. The force, that means we want to know how much the force being added to the mass here. Okay, so there's 2 kinds of the force. One is from spring, one is from damper. So combined together, the summed force is simply the force being transmitted. So basically, the force transmitted is this. Simply equal to k x dot minus y dot plus c as x dot minus y dot. Simply is this. Okay. And this one, if you plug into our equation of motions, and basically the two terms is what we're looking for, the transmitted force. So basically the transmitted force simply equal to minus mx double dot. Good. So if we want to estimate the magnitude of the force being transmitted, how much? Simply is this one. And if we know at the steady state, we know that x equal to capital X, this one, right? So mx double dot at the steady state with a minus simply equal to minus m omega square sine omega t plus v and capital X. This is the magnitude. Okay, and in our textbook, they're using F sub capital T. So here is defined here. So we define the magnitude is F of T, and that is this term. How to determine this term? You see that simply is m times omega squared capital X. We already have, in the previous page, we already determined the accelerations. So simply this term will multiply n y more, then that is this force. So basically all the information kind of propagated from the beginning slides, okay? Again, this is another graph. This graph is so look different than other thing else, but every time once we apply, look for this the information, then you can get using the right information. And so probably today we up here, and one little more section we coming up Monday, and so.